The next type of calculations we're going to look at is we are going to, using those molar ratios, calculate the mass of product that can be formed from a given mass of reactant. We last looked at problems how many moles of reactant is needed to form a given amount of product, or how many moles of each reactant are needed. Now we're going to take this one step further and put in grams. So these are going to be more multi-step problems. So we already know that the coefficients in the balanced equation are going to represent those molecule to molecule or mole to mole relationships. And when we do this in the lab, we can't say, okay, I need 5 moles of iron to give me a product. We can't measure moles, but we can measure is grams or milligrams of a substance, right? So we always are going to weigh out a certain number of grams, and if we want to know certain number of grams or milligrams, and if we want to know the amount of product from a given reaction, we can generally, let's say it's a precipitation reaction, we can filter out our precipitate from our solvent and dry it and weigh it on a balance to see how much we've produced. So it depends on what we're looking at and what conversions we need. So we can only measure grams. So we've got a way to figure out how many grams of a substance do I need to get a final amount of product, or given this amount of reactant, how much product can I actually form, or given this amount of reactant, how many grams of the other reactant is needed to completely react with our starting material. So there are a number of steps in mass calculations for reactions. We've already, we've looked at mole to mole ratios, right? We did that in a previous video where we wanted to know how many moles of reactant gives us a number of moles of product. But there are, if we want to know the number of moles of a substance that is produced or needed, starting from a given amount of grams, we can use the molar mass of a substance. So we already know that if I need to know the number of moles of a substance with a given amount of grams, I just use the molar mass. If I want to convert from the number of moles of a substance to number of grams, I'm also going to use the molar mass again, but in a different way, putting grams on top and moles on the bottom. So you've done those type of calculations as well back in Unit 5 when we were looking at solutions and we're going from grams to moles and moles to grams. Now, looking at equations now, balanced equations, we're generally going to take a look at this set of calculations where we're given a starting amount of grams, and the only way that we can compare substances is we have to get to the number of moles. So the only way we can get to the number of moles of a substance is first by using the molar mass. And then we need to use a molar ratio between the two substances to determine, how many moles of each is needed per moles of another. And then we can finally come up with the number of grams. So we've done all the first 3 calculations we've done previously. Now we're going to take a look at full out calculating the amount of substance that is either formed or required to have a reaction occur. So another thing is that we can go anywhere within this, you can use this schematic for any of these calculations. So if I need to know the atoms of a substance and the number of grams, I can start with the number of atoms, use Avogadro's number to get the number of moles, and then use the molar mass to find the number of grams. If I'm starting with the number of moles of a substance, I can use a balance equation to determine the molar ratio, and then figure out the total number of grams that's formed. So you can use this map to help you plan out what you're actually looking for in your calculation. So what is our plan? We start off with the grams of nitrogen, and from the grams of nitrogen, we're gonna go to the moles of nitrogen, and in so I need the molar mass of nitrogen. So, and I'm gonna put 1 mole on top per 28.02 grams of nitrogen. Next, I need to get from the moles of nitrogen to the moles of ammonia, and that ratio is going to come from our balanced equation, and it's going to be 2 moles of ammonia per 1 mole of nitrogen. So 2 moles of ammonia is produced per 1 mole of nitrogen. And now I need to know the grams of ammonia. So in that, I'm going to use the molar mass, and I'm going to put the number of grams of ammonia over 1 mole of ammonia. And that's a pretty simple calculation. That is 14.01. If we look at our periodic table, we know we have 14.01 grams for nitrogen, and then we have 4 times 1 point. Is this the eraser button? Nope, not the eraser. Okay. So that's 4.01 grams of nitrogen and 4 times 1.01 grams of hydrogen. So that's 4.04, so that's 18.05 grams per mole for ammonia. So let's set up our problem. We need to know the number of grams of ammonia. It's NH3, not NH. So it's 3 times 1.01 grams. So we get 17.04 grams per mole. So I keep writing the ammonia the wrong way. It's NH3, not NH4. All right, so starting with what we were given 32 grams of nitrogen. We're gonna use our first conversion, which is 1 mole of nitrogen is 28.02 grams of nitrogen. Remember, nitrogen gas is N2. Next, we're gonna use our second conversion, and there are 2 moles of ammonia produced for every 1 mole of nitrogen that reacts. And then finally, we're going to use our third conversion, in which we have 17.04 grams of ammonia per 1 mole of ammonia. Let's check to make sure we put everything correctly. Our grams of nitrogen cancel, our moles of nitrogen cancel, moles of ammonia cancel, and I'm left with grams of ammonia. How am I going to put this in my calculator? 32 times 2 times 17.04 divided by 28.02. So you're going to multiply all the way across the top, divide all the way across the bottom. Do not multiply, divide, because you're most likely going to end up with the wrong number. So always multiply across the top and divide across the bottom. And from this, you put all of that into your calculator, you are going to get 39 grams of ammonia. Remember, we need two significant figures. Okay? Last, we're going to take a look at the limiting reagent and percent yield. And in any chemical reaction, reactants are rarely converted completely to products. So what we know is that if we want a reaction to go to completion, we always have an excess amount of one reactant so that the other is completely used up. There are times in which we may not have all. So there are times when we only start with a certain amount. We only have a certain amount of starting material, and one of them is going to be used up, and one is left over. And so that's considered the limiting reagent. And we're going to define the limiting and excess reagents, theoretical yield, percent yield, and we're going to actually calculate theoretical and percent yield for a reaction. The percent yield now is just the ratio of the actual to theoretical. A percent, remember, is always going to be one number divided by a whole times 100. So the percent yield is going to be the actual amount that we collected by experiment. And so that's by experiment. Experiment. And the theoretical yield is what we get by calculation, right? And so we can use this percent yield as a conversion factor, like we did when we were looking at percent concentrations. So let's practice here. Notice that in this question it says when 26 grams of acetylene is burned in sufficient oxygen for a complete reaction, the theoretical yield is 88.80 grams. Calculate the percent yield if what we actually get in the laboratory is only 72.4%. So when you're in the lab, you give this percent yield as a way to describe your error in your lab, in your data collection. So percent yield is equal to actual over theoretical times 100. So we say 72.4 grams divided by 88.0 grams times 100. And we end up with the value of 82.3%, 3 sig figs. And so what we can say is that this reaction is 82.3% efficient. So the efficiency of this reaction is going to be 82.3% because this is our percent yield that we normally get for this reaction.